I am Crystal Hopper. I actually recognize most people in this room, but I am our OSGC, which is Oregon NASA Space Grant Consortium, PRISM's project coordinator here at SWOCC. And I assist Dr. Coiner with various things for our physics and engineering department. And we very much appreciate you guys coming to attend this lecture, and so grateful for Dr. Lazzati to make the trip over here to speak with us. We've got a lot of exciting things happening over at the department. We've got our awesome team of student researchers, which we call SPEAR, working on all types of neat projects. They're looking for micrometeorites. We've got CJ right here, and he's just doing a fabulous job on finding never before found asteroids with a really neat program. We have next Friday, we're going to be actually launching another high altitude balloon and doing some atmospheric research. So if you are in the area or want to kind of check that out, everybody's welcome to attend. We're looking for launch time around 11:30, I believe, next Friday, and it's going to be out here in the quad. So, but we have this summer, we're actually setting up a STEAM academy for kids from 7th to 11th grade, and we're working with all different professors and staff members within the university within this college on all types of STEM projects and activities are going to be doing that week. And that is going to be coming this August. So be listening for that if you've got some kiddos that are excited at those types of things. But I don't want to take up too much time. Got so much I could probably go on forever about it. But I appreciate all of you guys for being here. And here is Dr. Coiner. Thanks.
Well, as Crystal said, thank you to everybody for coming, and thank you to everybody for tuning in on our live stream. I had the opportunity to meet Dr. Lazzati a few years ago during one of our Oregon Space Grant Consortium meetings. I know he has a lot of experience with the field of computational astrophysics, but when I start hearing about astrophysics and cosmic explosions, that's always one of the things that I always like to use as kind of a gateway to get people into science, because it's one of the cooler topics. So I was very glad that he agreed to come down and give a talk. He's currently the department head of the Department of Physics and a professor at Oregon State. And I know he has a research group of students that are working on various computational astrophysics with gamma ray bursts and gravitational waves and assorted things. So without further ado, Dr. Davide Lazzati.
Thank you. Well, thank you. Thank you for having me. It's a pleasure being here. Thank you for coming, both those who are here and those who are following the live stream. My name is Davide Lazzati, as Aaron nicely introduced me. I'm from Italy, so I have a little bit of an accent. Hopefully that's not going to get in the way. But if it does, just stop me and I'll repeat exactly with the same accent what I just said, but slower. So I've been doing astronomy and astrophysics for about 25 years now. Let's not go into details about my age, and I've been really fascinated by cosmic explosions since I was about 18 when I decided to be an astrophysicist. I wanted to be a truck driver before. It's a little bit of a jump, I know. So today we're going to talk about gamma ray bursts, but really I want to talk about a few more things. And can I walk around a little bit, or should I stay in front of the mic?
Does the sound pick up? Okay, yes.
I'll try to hover around this area. I tend to walk a lot when I'm a little nervous. So I'm going to also use gamma ray burst as an excuse to talk about cosmic explosions in general, and also to tell you about why they are important. On top of being, of course, the most exciting thing that happens in the universe, they also play a very important role in making the universe what it is. And so I'd like every astronomy talk, I'm going to start from the real beginning. I'm going to start from the Big Bang. Why is the Big Bang important when we talk about cosmic explosions? Well, it was the biggest ever explosion, but that's not the point here. So the universe was born in this big fiery explosion about 14 billion years ago. What is important for understanding the role of cosmic explosion is that the universe was formed much simpler than it is now. You probably know that all matter is made by atoms at the microscopic level, and there are about 80 to 90 naturally occurring atoms in the universe now. But when the universe was born, there were only two. There was hydrogen, which is the one up there with only one proton and one electron, and helium, two protons and two electrons. So it's kind of trying to build this Harry Potter Lego castle with just black and dark gray. The universe now is, of course, much more colorful and full of different things. Here, for example, I don't even remember what I put up there. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. That's oxygen. I did it easy for myself. And that's probably iron. I'm not going to count. I'm going to guess there's 26 electrons there. And so the universe started with only two types of atoms and now has about 90 or so. Incidentally, one of the things that really always fascinated me about the universe is that we can tell what atoms are around there. And the reason is that atoms, they have like a fingerprint. They absorb light at very, very specific colors or wavelengths. And so if we look at a star, no matter how far from us, when we see these kind of dark lines, those are specific colors or wavelengths that are absorbed. And each atom has its own peculiar pattern. So we can recognize who's absorbing. And so what is the composition of the star or galaxy or nebula that we're looking at. And the things that always fascinates me is that despite how big the universe is and how far and wide we have explored, we've never ever seen any evidence of something that is not on Earth. Every atom that exists in the universe also exists on Earth. So, I'm sorry for the Star Trek fans, there's no dilithium. There's really no uranium. I think there's a few that in the various science fiction and fantasy series pop up here and there. No, unfortunately, there's no evidence of any other atoms. And to be quite honest, there's also no space for any atoms because atoms are different by the number of protons they have, and we just have them all, 1, 2, 3, 4, 5. There's nothing you can fit between 3 and 4. They come by whole numbers. Still, there's 90, and we need to explain them. How do we go from 2 to 90? Another thing that is important, and we'll come back to the meaning of this plot. I was trying to find a colorful version of this, and I couldn't. It's just very sciencey and black and white. But what is shown here, what is the take-home message of this plot is, nature has always a very easy time going downhill. Like a drop of a rock, it goes down, and then it goes up. And here you see the various atoms. Oops, sorry, wrong button. The various atoms from hydrogen all the way to uranium. There's iron here. And so what this graph shows is how strongly bound their nuclei are. Or in less sciencey words, if the universe wants to put together, I did it again, put together 2 hydrogen atoms to form a helium atom, that is easy. It's downhill. 2 lithium atoms to put a carbon atom, easy, downhill. All the way down to iron, it's easy to form atoms. Or in other words, you put together the small atoms, they fuse, they become a bigger one, and you get energy out of it, which is the way the sun shines. The sun produces its energy by fusing hydrogen atoms into helium atoms. It's a big drop. That's why the sun is bright. There's a lot of energy out of it. And nature can keep going on down to iron. The problem is that it gets very, very difficult to produce any of the heavier atoms, like lead, like gold, platinum, uranium, plutonium. It's not downhill anymore, it's uphill. And so that's where quantum explosions that we see come to play. And there's also this little ripple here. We'll talk about that ripple towards the end of this presentation. Okay, so explosion. How do we know there are even explosions in the sky? If we look at the sky tonight and tomorrow night, but maybe not in Oregon. Yeah, there's going to be clouds both nights, most likely. If we go across the Cascades to the desert and we look at the sky 2 consecutive nights, now the stars might have moved a little bit only because of the motion of the Earth, but truly the sky appears identical. And so here I have 2 pictures of the same galaxy taken 2 nights apart, and as you can see, they are identical. Are they? Is there any difference? There is. Did you say yes? Which one? That's the button. Down there. And please show. That one. Congratulations. It usually takes me 15 minutes. Unless I prepare the talk to others. So there is something new. And it's not typically something that we can see with our naked eye. Those are faint new stars because they come from very distant galaxies and took a telescope here. But yeah, it happens. And quite often, there's actually many of these new sources of light that appear in galaxies every day. This particular case is a supernova, which is a star that is more massive than our sun, that runs out of fuel. Basically, all the hydrogen has been turned into helium, and all the helium into oxygen and carbon, and all the oxygen into silicon, all the way to iron. And then we are down at the bottom of that boring black and white plot that I showed before, and it's really hard to fuel a star with that anymore. And the star implodes and explodes. We could spend the whole night talking about why it does implode and explode. I'm going to ask you to please trust me on that for the moment. But that's what we see when that happens. So this was a star maybe 10, 20 times more massive, with 10 times the mass of the sun, that ran out of fuel and went kaboom. Now, so I said these are difficult to see. They happen a few per night. There's another type of explosions that are not as common, maybe only 1 per night or 1 per week, but are much brighter. These are gamma ray bursts. So these are 2 animations of the same gamma ray burst. And what you see in this reddish hue is the observation in gamma rays. And in the kind of black and white on the right, for you is the right, you see the optical visual light image. So gamma rays. So this is a gamma ray burst. and it's called gamma ray burst because it does produce a lot of gamma rays. So what are gamma rays? Our eyes are sensitive to light or visible electromagnetic radiation. There is much more to electromagnetic waves than light. We are familiar with many of them. We are familiar with infrared radiation that gives us the sensation of heat. We are familiar with microwaves. We use them in the little oven to warm up the milk in the morning. We are familiar with radio waves that we use when we listen to the radio. And on the other side, we are familiar with ultraviolet radiation that gives us a nice tan skin in the summer. Not in Oregon, maybe if you go to Florida. And X-rays when we go to the doctor and take an X-ray to see the bones. It doesn't stop there. There's an even more energetic kind of radiation. It's called gamma ray. It is not healthy to be exposed to gamma rays. And luckily, the Earth is surrounded by the atmosphere that blocks the gamma rays from the universe. But if we fly a satellite with a gamma ray detector, which is what has produced this animation, and we just observe the sky, most of the time, all we see is this reddish band here. That's the gamma rays that our galaxy produces all the time. But then about once a day-ish, there is a new source that appears in gamma rays. And what makes this spectacular is that you may notice that when this new source reaches its brightest moment, it completely outshines everything else. It's coming, not yet, there it is. Right, so the galaxy disappears for a moment. It's kind of like when the sun comes up in the sky. It's not that the stars disappear, the stars are still there, we just don't see them because the sun is so bright. And so a gamma ray burst in gamma rays has the same effect. It's so bright that the rest of the universe disappears. So they're very easy to spot in gamma rays because they are obviously there when they happen. This is not any gamma ray burst either. This is the brightest, the most energetic gamma ray burst ever detected. It was so bright that it is by far the farthest object in the universe that has ever physically altered the atmosphere. So for a few seconds after this burst exploded, high-altitude radio communications were impossible. The military discovered it immediately because they use it routinely. And so this was so bright that ionized the atmosphere, the upper atmosphere of the Earth, and altered the way the Earth system works. Luckily, just for a few seconds. No, the next farthest thing is right in our galaxy, and this object came from halfway across the universe. Another record that gamma ray bursts hold is the farthest object by a lot that could have been seen without a telescope. And I have to say could because it wasn't actually seen by, as far as we know, nobody was looking in that particular patch of the sky at the right time. But we know that if somebody had, they would have seen for a few seconds a new star appearing and disappearing. And truly, maybe somebody did. They just didn't realize. Maybe they thought it was one of those Starlink satellites that you see turning on and off in the sky every night. So they are really spectacular events in terms of how much energy they have, how bright they are, and so how far away we can see them. For a few years before the James Webb Telescope was launched and started working, the farthest ever object seen in the universe was a gamma ray burst. Now that there are galaxies that are even farther away than that. But we can truly see gamma ray bursts practically at any distance in the known universe. So a few facts, just to make you say, wow. And I use the word extremely a lot here. So we said already they happen about 1 per day. That doesn't mean we see 1 per day, because we don't have a gamma ray detector that can look at the whole sky always. Typically there is the Earth that obscures half of the sky, then there is the sun that also interferes in one direction. So we look at about maybe a third, a fourth of the sky at any time. So we see about 1 burst per week. But if we correct for the part of the sky we don't look at, we know there have to be about 1 per day. One reason why gamma ray bursts have been really difficult to study is that they don't last long. They only last up to a few tens, maybe 100 seconds. And then they disappear. And so you barely have time to kind of pick up the phone and call the telescope, hey, there's a gamma. Oh, never mind, it's gone. And so for 30 years, they were very mysterious. Now, we don't have anybody picking up the phone anymore. It's a computer that sends out the notice that it was a gamma ray burst. And so we can follow them. If not, when they are still in those very bright few tens of seconds, we can observe the place in the sky where they come from weeks and months later and still see the sign that they did explode. As we said, they're very rich in gamma ray radiation. That's why we call the gamma ray burst. And so we have to launch satellites in orbit to observe them. They are very, very far from us. One thing, and we'll come back to that in the next slide, they come from very, very small region in space, much smaller than the Earth, for example, which is a problem because if we try to figure out how much total energy is required to make a gamma ray burst, we see that it takes about the entire mass of the sun multiplied by c squared. So the famous Einstein equation, E = mc squared. To make that E to be equal to the energy of a gamma ray burst, we need to put an m there that is the mass of the sun. Yet, we cannot take an object that is as big as the sun to produce a gamma ray burst. We know the region of space that makes a gamma ray burst has to be much smaller. So somehow, we need to take about the mass of one sun and shrinking in a region of space that is smaller than planet Earth. It is interesting how we know that. And so I wanted to walk you through that. It has to do with variability. So how quickly the brightness of gamma ray bursts changes. So the idea is, and maybe before I start, I should make it clear that there is no way, because of how far gamma ray bursts are, there is no way that our telescope can resolve them. So it's not that we see, oh, look, that thing is like 10 meters across. No, every gamma ray burst is just a point. There's no way we can tell how big they are by looking at an image of a gamma ray burst. We have to be much more imaginative. So the idea is the following. Suppose we take the sun, and let's imagine that we have the magic wand like Harry Potter. Yes, I have kids that are about 10 years old. That's why I talk about Harry Potter all the time, and Lego. We have the wand of Harry Potter, and we make the sun become twice as bright in an instant, like a flash. Would we see a flash if the sun flashes? No, we would not, because the sun is big. And so when something is big and we are looking from one side, even if the sun itself sends light in our direction in just a flash, because the light that comes from the nearest side of the sun has to travel a lower distance than the light that comes from the far side of the sun, what we see is the sun getting brighter for about 4 seconds and then dimming again for another 4 seconds. So the fact that the sun is huge, is about 4 light seconds across, turns even a flash that the sun might intrinsically produce into something that is slow in changing. And if the sun would do that, this is about what we would see. So this is about 4 seconds that it takes the sun to get brighter and then get dim again. And this instead is a gamma ray burst. It changes much faster. This is actually a true gamma ray burst that I converted into screen brightness to give you the impression. Right. So again, this is the sun, slow, and this is the gamma ray burst turning on and off many, many times in a fraction of a second. Actually, the brightest pulses or flashes coming from gamma ray bursts are about 1 millisecond. And so the region of space from which the gamma ray burst is coming has to be about 10,000 times smaller than the sun, which is even smaller than the Earth. So it's kind of a conundrum. We need to take as much mass as there is in the sun, stuff it in a region of space that is smaller than the Earth, and then make it go kaboom. This is 200 years of stellar evolution in one slide. So how do we do that? Let's go through these a little bit. Let's see how, we should have enough time. So what happens to stars? We have stars of, as you probably have understood by now, we have stars of different mass and size. Our sun is about a middle sized star. We measure the mass of stars by comparing them to the sun. So the sun has 1 solar mass, which is kind of there's not much to say there. It's the sun, it has its own mass, so it has 1 solar mass. There are stars that are smaller than the sun, down to about 1/10. They are smaller also in size, as I've been trying to convey here. And eventually they will die, but they will die kind of peacefully. They run out of fuel, they shrink, and they become what we call a white dwarf. So it's a very compact object, about the size of the Earth, and is white because it gets very hot in the process of contracting. Totally speaking, it hasn't happened yet in the universe. Stars that are about half to 1/10 the mass of the sun, they take a very, very long time to run out of fuel, much longer than the life of the universe. So they're still there. Even the first that formed is still there, looking orange, hasn't gone through the shrinking. Something that has happened instead is the death of stars like our own sun. They will run out of hydrogen as well. And the consequence of that is that the central part of the sun is going to shrink. But the outer layer, they're going to kind of like a slow motion explosion. They're going to be ejected and get very, very big. They'll form what is called a planetary nebula, which is this object here. It has nothing to do with planets, but is astoundingly beautiful to look at. Some of the prettiest pictures of cosmic objects are planetary nebulae. If you go to the Hubble Space Telescope gallery, just go to the planetary nebulae. Ignore everything else. But maybe not quite. There are some supernova remnants that are pretty cute too. But the planetary nebula, come on. Full of colors. So this thing is now so big that all the planets have been engulfed and vaporized, and hopefully by then we have interstellar travel. If it's not with dilithium, some other way, but hopefully we managed to leave planet Earth for some other habitable world. Eventually, also the sun will become a white dwarf. That's in about 5 billion years, so nothing we should worry about. Things now get really interesting when we look at stars that are much bigger than our sun. The biggest possible star is a few hundred times more massive than the sun. Stars cannot just grow indefinitely. There is an interesting property that if a star produces too much light, it blows away its own gas. And so because when we put more mass in a star, it becomes quite rapidly very, very luminous. It gets to the point that it's just the biggest star, the one that is about 200 times more massive than the sun, is just barely there. If it gets any bigger, it will blow away itself. Not in an explosion, but kind of in a wind. Like I'm using the word blowing kind of literally, like. Anyway, but so things that are now 10 or more times bigger than the sun, what happens? Well, it depends. Some of them are just a little bigger, 10, 20, 25 times bigger than the sun. They're not, why did I say they're not? I don't know. They are going to explode as supernovae. Now, remember that pale blue dot of light on the galaxy that you were much faster than me in seeing in those images. That was a supernova. So it's a star 10, 20 times more massive than the sun, and runs out of fuel. The core implodes, and the rest of the star blows up. One important thing of supernovae that is different from gamma ray bursts, we'll talk in a moment, is that supernovae explode in all directions, not as you can imagine, this light yellow thing is gamma ray bursts that explode only in one direction. So supernovae kind of boom in all possible directions. For that reason, they appear to be less energetic than gamma ray bursts, and they are slower. So the material that is sent out in the supernova explosion only travels about 10,000 kilometers in a second. Still pretty fast, faster than my electric car, but it's slow in cosmic terms. Eventually, what's left after the explosion kind of dissipates is something that we call a neutron star. And now we start talking because a neutron star has the mass of the sun, or maybe even more, and it's tiny. It's about a few miles across. Kind of covers Coos Bay, maybe. Maybe it would sink in the bay. So we're getting to something that has the properties we need to make gamma ray bursts. It turns out they'll be important. But there's still, we have to talk about the really, really big stars. And here there's a little bit of a mystery, because there's a lot of very big stars. But there's many, many more big stars than gamma ray bursts. And so it's not enough for a star to be really big, like 50, 100 times bigger than the sun, to make a gamma ray burst. There has to be an extra ingredient. We think that it has to do with how fastly they spin. So a star that is very big and very spinning like a top will not make a neutron star, will explode and will leave behind a black hole. And in the process, will make a gamma ray burst. Now you might ask, oh, but if it's still a star that explodes to make the supernova or the gamma ray burst, and yeah, you're saying 20 solar masses, 50 solar masses, it's about the same. So why is the gamma ray burst so much more powerful than a supernova when the tank is about the same, the engine is about the same? There are two reasons. The main one is the beaming. And to have an idea, think about this laser. This laser is about 5 milliwatts power. And it still can blind you if I shine it straight into your eye. The lights are about 50 watts. So thousands of times more energy than the laser, and still you can look at the light without any harm to your eye. And the reason is that with the laser, it's only 5 milliwatts, but it is all concentrated in one direction. So it appears that there's much more energy there. And the second thing is gamma ray bursts are extremely fast. The material ejected in the gamma ray burst explosion moves about at the speed of light. And so for that reason, what we see lasts very short. If you remember both the red diffused animation I showed you or the one of the flashing white light, a few seconds. A supernova takes weeks. And so not only the light, the energy of a gamma ray burst is concentrated by taking all directions and squeezing them into a narrow beam, but also by taking 1 week, 2 weeks of time and squeezing it into a few seconds. So that's why gamma ray bursts appear and are so extremely bright. The last thing I wanted to talk about that is really exciting and is something relatively new that only started happening about 5 years ago is related to the fact that stars, especially the big massive stars, those that go supernova or gamma ray burst, they are very rarely born in isolation. They tend to be born in multiple systems. So 2 stars, 3 stars together orbiting around each other. So what happens to this schematic view of stellar deaths if we add the fact that stars are not isolated? Now, there is a very interesting consequence. Let's kind of fast forward to the time when we have 2 massive stars, they're born, they shine, they're bright, they go supernova, maybe gamma ray burst, and then we have those 2 either neutron stars or maybe a neutron star and a black hole left. They're very small, they're very compact, they're very heavy, and they are still orbiting around each other. Because of Einstein's relativity, they will produce what's called gravitational wave. So a ripple in space-time that propagates out and carries away energy. The consequence is that 2 stars not only orbit around each other, but the orbit becomes smaller and smaller. They get closer and closer to each other until they touch and they merge. And this phenomenon was expected to happen, but never seen before until we started becoming able to observe gravitational waves. And this is a spectacular event. It's still one of a kind. It was observed in 2017, August 17, just a few days before this total solar eclipse. You might remember that. So it was 3 days before, or 4. The eclipse was the 21st, right? Yeah. So 4 days before the eclipse, the squiggle down here, that's the gravitational wave signal. So it's these big antennas on the ground. One is up in Washington State, one in Louisiana. They pick up this ripple in space-time. They see how they get more and more intense, And the reason why it curves up is because they become faster and faster. Like when the two neutron stars are far away from each other, they circle around each other slowly. As they get closer, they also accelerate. And so that's what makes this yellowish signal curve up. And then the signal disappears, and that's when they merge. And then 2 seconds later, gamma rays. Right? These are two different satellites. One is called Fermi, one is called Integral, so completely different instruments. They both see at the same time an excess in gamma rays. This is not a super bright one, but it's clearly there. And so we've seen something that produces both gravitational waves and gamma rays. And it has all the properties of a gamma ray burst. It only lasts, a couple of seconds. It's bright, it disappears, there's nothing left, or almost nothing after the gamma rays are gone. And so here's where the story becomes a little more interesting. Something I haven't mentioned is that there are two kinds of gamma ray bursts. Those that last more than a few seconds, they're called the long gamma ray burst. They can last up to 100 seconds. But there is other class of gamma ray bursts, they're called the short gamma ray bursts, and they usually last 1-2 seconds or so. All what I've said until now, the massive stars, wrong direction, the black hole, the big star, it all happens in long gamma ray bursts. Short gamma ray bursts come from this other mechanism when two neutron stars crash onto each other and merge and become a black hole. And so until 5 years ago, it was a very nice theoretical model, unproven, never observed until LIGO came about. LIGO is this gravitational wave antenna. Really interesting. I like to compare a gravitational wave to going to the doctor. Well, I like to compare astronomy to going to the doctor. When you go to the doctor can look at your symptoms, and that's like taking a picture of the sky. Or the doctor might decide to take an X-ray, and that's kind of like looking the sky in the X-rays or in the gamma rays. You start getting a little deeper in things. The next thing the doctor does is take an MRI. We don't have MRI in the universe, but luckily we have gamma ray. We have gravitational waves. Gravitational waves is like the MRI of the astronomer. Nothing stops gravitational waves. They come out of anything. They are made by matter, and so matter cannot stop them. And so they really let us go and check what is happening in the core of stars, in places where no man has been before, no man has seen before. We can now access them with gravitational waves. Circling back to our elements and where do the gold, the platinum, the uranium comes from. It turned out we look with our telescopes at the location of these special gamma ray bursts with the gravitational waves, and there was something else there. It's called a kilonova. So it's not as bright as a supernova. So it's a kilo, it's less, about 1,000 times less bright. But what is really interesting about the kilonova is that it's an explosion that happens because two neutron stars are merging, and so it happens in a region too much details. Neutrons are really important to climb up that uphill slope and build the heavy elements. And so I want to leave you with this image. I love it. It's on Wikipedia. It's not a secret image. This is the periodic table with all the elements in the universe and on Earth. They're the same elements, as we said, but they are color-coded. And here there's hundreds of years of research of thousands of astronomers and astrophysicists. And they're color-coded based on where is that element produced in the universe. And so, as we've said, everything that is blue is made in the Big Bang. And yeah, it's hydrogen and helium, and maybe a tiny little bit of lithium, but who cares about lithium? It's not dilithium. Okay, sorry, that's a joke. Then there are dying low-mass stars. What is low-mass stars here is like the sun. So these are the elements that are produced by stars like the sun while they fuse hydrogen, and then they are given back to the universe by those beautiful planetary nebulae. And so some of the common light elements, especially carbon and nitrogen, are produced in stars like the sun and then released into space. There's also some of weird heavy elements like strontium, ytterbium, zirconium. I have no idea. Nobelium? Nibium? I need a chemist. Not for astronomers. The universe is made of hydrogen, helium, and metals. Everything else is a metal. And then, so there's supernovae, the yellow kind of mustard color thing. A lot of important things come from supernovae: oxygen, aluminum, silicon. All your computers, all the silicon in your cell phones come from a supernova explosion, and so on. But then, if you really want to know where your jewelry comes from, silver, gold, platinum, they're all purple, or predominantly purple. So they do come from these kilonovae, of these neutron stars merging. So it is mind-blowing to me, thinking. I'm wearing something in my hand that comes from a binary neutron star merger. Or when I eat a chocolate bar, chocolate is carbon, nitrogen, oxygen, and hydrogen. There's Big Bang in there. There are stars like the sun, and there are supernovae. They taste kind of delicious. Okay, so I could talk about this graph for the next 6 hours, but I'm going to do that to you. So thank you very much for walking with me through this history of the universe, its nucleosynthesis, and stellar explosion. Thank you.
Well, thank you everybody for attending. For those of you in the audience, we'll do Q&A here in just a minute. I wanted to remind everyone on the live stream and in the live audience, we do these events usually about once a month. Due to some travel in May, we won't have one in May, but we'll have one in June. But the one in June will actually feature our student researchers here at SWOCC that will be presenting their own work. I've got a team of engineering students that are working on an electric aircraft and printing a model of a propeller that's going to be using a magnetic induction system to try to recoup some of the energy from the propeller that we will be talking about. We'll also be talking about our discoveries with Isaac and the asteroids, as well as starfall and the micrometeorites, and a few of our other projects that we're currently working on. So that will be June 1st. Please come out and support our students. Please tune in on live stream like you have today. Show our student researchers that we have that level of support. We also, again, thank everybody for coming. One of the things we do have over as you go, if you haven't signed in, please make sure to sign in. It helps us keep track of essentially the number of people that are here, and we also have a way to track the number of people that are on live stream so that we have an idea on these types of programs. If you like seeing these types of guest speakers to come in, we also have a small donation jar if you're interested in facilitating more of these programs. We humbly ask for any donations that you may be willing to part with. We appreciate everything you guys do. And with that, I will open everything up to Q&A. And if you have questions, then feel free to stand up, and then we can hear your question. And then Davide, when you get a question, you might repeat it just for the audience that's listening.
Will do. Thanks.
Doctors, we could get fancy and grab a microphone for the audience.
We could.
Huh?
Yeah, we could. I forget where it is, though.
I got it. I got you. Excuse me.
You're also faster at running around than I am.
I can use it. Okay, that works. Anybody? Please use my phone. Just went through the whole thing. Any questions?
I probably have 1,000 questions.
Oh,
I can't think of
start with
anything.
one.
No.
No, I know. Anybody else?
I'll ask one from off camera right quick, because I usually use this one because at the end of all the talks. So you said when you started, you thought originally you were going to be a truck driver, and then you got really interested in doing astronomy and astrophysics. So as students that are in the audience that may be interested in looking into astrophysics, what advice would you give them as they're getting into their studies, and how to drive them sort of in that direction?
Don't like trucks too much. So the question is, what advice can I give to students who might be interested in astronomy? I really like this question for two reasons. But one is because I'm passionate about astronomy. And so the recommendation would be, there's a lot of physics in astronomy, and there's a lot of math in physics. So that's where you want to really concentrate your attention and your studies. But the other thing is that Oregon State is actually working into creating a major in astronomy and astrophysics. That would be the first in Oregon. So if you're interested in following your studies and learning more about astronomy, look north. It's going to take us just technical time. It's probably going to take us about a couple of years to get that going. But we do have a really fast-growing group. We have now 3 tenure-line astrophysicists. Some of our instructor team also has interest. We will be hiring more astrophysicists next year. And so Oregon will finally have an astronomy program. There is none in the whole state, probably because it's always cloudy.
There is that.
Or we have radio astronomy.
That's right. Or you can go out to the desert.
No. Oh, you did? Well, try to.
So one of your slides kind of showed the mapping of gravitational waves, and then like the bottom was from like a ground station that was mapping it, and then I believe the above were from like different different satellites tracking the gamma radiation. So I guess, guessing like in the future when we're trying to do that, we're going to be using those two in pseudo, kind of like together. But like, what necessarily are the differences in using those two? Like, what are the differences in tracking gravitational waves with gamma radiation versus like the machine?
So the first difference is that gamma rays and gravitational waves are two different things, and they can come together from some stellar explosions, like short gamma ray bursts, but not necessarily. And so there are a lot of situations in which we only see gravitational waves with the ground antennas. And that's, for example, when two black holes merge. LIGO has detected, I think, a few hundred gravitational wave signals right now, and there is certainly one, maybe two, that also have the gamma rays following. And on the other side, we have thousands of gamma ray bursts that do not have a gravitational wave. Those that come from massive star explosions don't. So we need to be very careful to combine these two things when having them together bring us something, but not just limit ourselves to just look at the two things in coincidence. Something really interesting that was seen in that image was that delay of a few seconds. The gravitational waves arrive, and then a few seconds later, the gamma rays. And something we're really curious about is whether it's always 2 seconds or maybe it's going to change, and why. It's kind of amazing how both the gravitational wave and the gamma rays have traveled for 120 million years. And they could have gone at different speed, and so they would have arrived at completely different times. And instead, out of 120 million years, they are only separated by 2 seconds. Scientists don't really like when those fine-tuned things happen. So we do need an explanation. And we don't know. There are a few options, and seeing more events will help. Like, one option is the gamma rays go a little slower, and so if we see another event that comes from farther away and there's more delay, that would be it. But probably that's not the right explanation.
Do we have any other questions in the audience? You did come up with one. You said you had 1,000 words.
I didn't know.
Okay, I'm so sorry.
Oh, no,
You know, this is all my fault.
Early in your slides, like 5 or 7, it was showing the different, going down with the different, I guess, frequencies and the light emitted. You're talking about, I can tell everything, composition by the wavelengths. I was wondering, if we're looking at stuff, no matter how far away, if it's like lower, like it's mostly like helium, hydrogen, does that mean it just hasn't made it to like something more heavier? And it's just like early stage development. And if we could look at it, later, it would be like something, everything like heavier.
So we do see some stars that are extremely old, and those are virtually only made by hydrogen and helium. And so things become heavier. To have the heavier atoms, to see a star that has gold or uranium in it, in the gas, we need to see a star that is not what we call a first generation star. Right? So the universe is all made of hydrogen and helium. And then you form the first stars. And the first stars are made of hydrogen and helium. And then they explode and they start sharing with the universe all the heavier elements that they're doing. And then you have a new generation of star that have some of these heavier elements. And then you can have a star with more massive atoms. something that's really interesting is that if what I told you is true, let me go back one slide. So there's a lot of supernovae, and there's very, very few neutron stars merging. And so because of that, you would expect that elements like oxygen and neon and silicon, they are very uniform in the universe, while how much gold you have really depends on whether you're close to where a binary neutron star merged or not. And this is what we see. If you look at how much oxygen there is in various stars, they're all about the same, except the very, very old ones that have not. While if you look at how much gold there is in stars, different stars have incredibly different amount of gold. The Earth is about average at the sun. So we are not too lucky with how much gold we have, but it could have been worse. Does that answer your question?
Further questions from audience members?
Yeah,
We're gonna keep going.
I did have one more based on what you said about the astronomy degree coming to college. Would that be a degree that we could set up? This is more for me, but it would be one of these things that I would like to set up for the college. But would it be something that we could set up a program where they could start here and then transfer into that astronomy and astrophysics program, or would it be one of those things that would have to start here?
I imagine it's going to be the first that students can transfer in. The department, half of our graduates in physics are transferred from community colleges. And now it's just for the degree in physics, for a major in physics. I don't see any reason why the major in astronomy would be different. So, yeah.
Yeah, it's really exciting. That's like something that we have been talking for a long time, and I know that Dr. Pointer has been working on. Astronomy has always been something that everybody's excited about, and I'm really surprised that we don't have anything yet for Oregon, in the state.
So it's
So,
always cloud.
but even to the youngest kids, we now have this K-12 STEM outreach program, part of Prisons, and we'll go talk to the kids of all ages, and I'm telling you what, astronomy, that's like gets everybody so excited, and it's the same with us though. We love it. So it's awesome.
Good. Well, hopefully it will be a good service for Oregon.
Thank you.
Sorry, I get the
Yeah, I know, right?
I have all those gamma rays in my face.
Yeah. Well, if we don't have any more questions, then I will thank everyone again for coming, and I'm sure Dr. Lazzati will stick around for a few minutes if you have questions that you that come up as you're leaving. But please feel free to sign in. We have free stuff we have free NASA things that you're welcome to take with you if you want to. And remember to join us next time for our students symposium on June 1st.